and welcome to The Sky at Night, although this programme is about the sky by day.
That's because we're talking about the Sun. It's just an ordinary star, one of billions in our Milky Way galaxy, but it's important to us here on Earth because it provides our heat and our light.
We've come to the Royal Observatory Greenwich to tell the story of our Sun, the monarch of the solar system.
And Chris North will have news from the very edge of the solar system, where it turns out things are a little bubbly.
And Pete and Paul will be giving advice to some newcomers to solar observing.
Astronomers have been studying the Sun at the Royal Observatory Greenwich for more than 350 years. It was their job to measure the midday sun with their transit telescopes, setting the watches of the city, the country, and the world. The meridian ball still drops at precisely 1 p.m. The first Astronomer Royal, John Flamsteed, is still remembered today in the name of the Flamsteed Society, the Royal Observatory's resident amateur astronomy group. Today, they're setting up in the courtyard for some solar observing. Protecting your eyes when looking at the Sun is critical, and these telescopes have astronomical filters to make them safe. Pete and Paul are finding out how we can look at the Sun safely, although today it's proving rather elusive.
So Rupert, talk me through what you've got set up here.
Okay, well this is just a conventional nighttime telescope,
right.
Refractor, but to allow us to view the Sun, we just have this homemade filter.
Right, okay.
Uses a special material, which is safe to look at the Sun. So using that will give us a white light image. So you see all the sunspot detail,
right,
and any surface granulation. So it's quite an enjoyable and simple way to observe the Sun.
What sort of telescope is this?
This is a hydrogen alpha telescope.
So this is, unlike when we're looking in white light, this gets all those lovely red images. It sees further into the Sun, doesn't it?
It does.
What do you enjoy most about solar observing?
I think it's something you can do in London without any light pollution, and we can do this here the same as we can do anywhere else in the country.
Yeah.
We can do it in the daytime and keep warm, unlike not
hoping
today.
to look like, hoping to see it myself, but it doesn't look likely at the moment. Well, Pete, we were hoping to do some solar observing today, and look at it, it's nothing but cloud and snow.
But we have got some footage we took earlier, and that really shows the dynamic nature of the Sun.
We have indeed. There's some lovely objects on there. There's some prominences and all sorts of interesting things.
But we should talk about how to actually get into solar observing, because it doesn't need to be an expensive thing to actually take up.
No, it doesn't. Let's look at the sort of very basic end of it, the white light area of solar astronomy, and should perhaps explain what we say is white light isn't really a colour. White light is in fact composed of all the colours of the rainbow. But you can see quite a lot of the Sun in white light. You see some interesting objects, can't you?
You can. It is a very cheap way of getting into solar observing.
It doesn't come cheaper than that.
Well, you get a piece of white light filter like this from an astronomical stockist for about £20 for an A4 sheet.
Well, that's reasonable.
And then you have to make it yourself. But once you've made it, you can then slip it on the end of a nighttime telescope. It converts it into a telescope which is safe for solar viewing.
It looks rather flimsy, Pete.
Well, it does, but it is actually quite tough stuff. But this rejects 99.9% of the incoming light from the Sun, so it reduces the Sun's levels to a safer value.
And when doing that, then you can see some of the things that you'd see, like sunspots. In white light, sunspots are quite dramatic. They're really dark, and when you get a lot of them clustered on the disk, they really can be quite dramatic, and watching them move over time, I think, is quite fascinating.
That's right, because you can see the Sun rotate, the effects of the Sun's rotation. You can see them slowly drift across the face of the Sun.
Well, let's move up to the higher end, i.e. your area, more expensive end. We're looking here at something like this. This is a hydrogen alpha telescope, so this is looking at one of those colours of light. And this returns those beautiful red images. I've seen those images of yours, Pete. Lovely red images of the Sun. You can see a lot more. The Sun takes on a completely different form in this, doesn't it?
That's right. You're looking at the sort of glowing hydrogen just above the visible surface of the Sun.
Beautiful.
And that's actually what our footage is about.
One of the things, as you say, that this sort of telescope reveals is just how dynamic these objects are.
Oh, that's right. I mean, when you're imaging the Sun, you can actually see changes in features after just a few seconds.
These incredible images are from telescopes in space, which stare unblinking at the Sun's raging atmosphere. The reason the sun, our star, is constantly changing is because it's a writhing sea of hot, ionised gas known as a plasma, and it's powered by a nuclear reactor in its core. The churning of the plasma strengthens the sun's magnetic field, causing it to burst through the surface and out into space. Dark sunspots are formed where strong magnetic field traps gas at the surface and it cools down. At Greenwich, they have been looking at sunspots for over 100 years. Marek Kukula is an astronomer with the Royal Observatory. Although he normally looks at galaxies, he showed me the telescope that was once used to document the sun's every move.
So this is a photoheliograph, one of several that belong to the observatory and were sent all over the world. And as the name photoheliograph suggests, it was used for photographing the sun. And I actually have here a glass plate that was taken using one of these instruments. It may even have been this one here. And this is from 1917. Ooh. And you can see it's a beautiful plate showing a negative image of the sun.
I can see on here that it says that it's taken in the K line, which means calcium K filter was used, looking at the chromosphere of the sun.
So this isn't the whole of the light coming from the sun, just a tiny fraction of it?
Just a tiny, tiny fraction, and it allows you to see a particular layer of the sun. And what's really nice is that you see these two bright regions here, and that's formed by the locations of very strong magnetic field, or sunspots. And
so my field is galaxies, not the sun, so I'm kind of... these look bright, but it's a negative image, so they're actually dark.
So they're actually dark, that's right.
Right, so they are sunspots.
These are the sunspots. And what's really lovely also is that they're near the centre of the sun. And since sunspots produce big eruptions into the solar system, it might be that these sunspots, back in, when's this, 1917, produced an eruption that reached the Earth and triggered the Northern Lights. We'd have to check the dates.
The early work by Greenwich astronomers established that the sun has a cycle. They were able to see a pattern in the number of sunspots, where the number rises and falls roughly every 11 years. Called the solar cycle, it has a maximum and a minimum, where the sun moves from being active to quiet and back again.
There is an archive of these images that were taken day after day here in Greenwich and at other royal observatories around the British Empire. And I guess they go back into the 1870s. Are these still useful to you as a solar physicist today?
They are. We're really, really interested in the solar cycle, but we want to know how the sunspot number has changed over the last decades, hundreds of years, I mean ideally thousands of years even. But the archive that Greenwich has means that we can check back to the 1800s and look at the sizes of the cycles, right. See, are they always regular, how do they change? And at the moment, even though the sun's at solar maximum, it has been showing that it's a little bit quieter in this cycle than it has been in previous ones, and that's a big question in solar physics to try and understand why that's the case now.
So the work that was being done on instruments like this back in the 1800s, that still actually has some relevance to solar physics today?
Still, the archive is incredibly important.
Well, it's good to know that Greenwich is still contributing in some way to modern physics.
I'd like to have a go on this telescope, I have to say.
We'll bring you back on a sunny day.
Seeing sunspots and other features evolve and change quickly is one of the pleasures of solar observing. Looking at the sun is something even beginners to astronomy can enjoy. Christina and Caroline have bought their first telescopes, and they want to know how to look at the sun safely. Who better to ask than Pete and Paul?
Over there we have Keaton, he's holding up the sun. This is your moment, Keaton, it's arrived.
He's been there for hours.
In that position. And so what we would do then, if we wanted to find the sun, the first thing to do is to remove the viewfinder. So this one just slides off here.
Yeah, and that one
Why
too.
do you remove?
That's a good question. We remove it because otherwise the sun's light will come streaming down and it's enough to cause damage. So we want to be very safe. So before we go looking for the sun, the first thing we need to do is filter our telescopes, and I have some stuff here I grant you, looks like ordinary tin foil, but it's not.
So it's not the type in my kitchen drawer?
No, leave that in the kitchen drawer, because if you use that, blindness will result. We don't want that. So here you go, have a look. This is the sheet we tend to use. It costs about 24.
It's about £20 for an A4 sheet.
Yeah.
In fact, there's a filter down there, if you can grab that one. That's what you have to do, is take that stuff and with a bit of DIY using some highly technical cardboard, sellotape and scissors, you can make your own filter. And if you're wondering how you make that, we've actually got instructions on the Sky at Night website. So that's bbc.co.uk/Sky at Night. There is a little bit of film on there showing how to make that filter.
So once you've made the filter, how long will the filter last? Is it, as long as it's intact, it lasts?
If you look after it, it'll last for a long time.
You can always see if it's damaged just by holding it up and if there's any holes.
That's a very good point, actually. Yeah, before you put the filter on, it's always a good idea to hold it up to the sun so that if any light's coming through and it's ripped, throw it away and just make another one.
Okay, brilliant. If I didn't have a lot of time, could I not sort of just quickly put the foil over the front of it and put an elastic band round it that way?
That's an excellent question, and it brings up the fact that you can't do that really. You need to make sure that the filter fits securely over the front of the telescope, and it certainly can't come off. If the wind were to blow it off or the elastic band were to unfurl and it pinged off, that would be disastrous.
Okay,
absolutely don't do that.
So it's not worth cheating?
No, definitely not.
Once you put this over the top, do you have to tape it down or fix it?
I do. I always put a bit of sellotape on just to make sure the thing stays on.
It doesn't need to be a solid, just a tack of tape, or just to keep it firmly there, I think is a good idea, actually.
You can't be too safe, and why take the risk? So yeah, sellotape, no elastic bands, make sure the thing stays in place and no danger of it coming off.
On the Sky at Night Flickr page, you can see amazing images taken by amateur astronomers. They show material lifting off the sun, called prominence eruptions, explosions called solar flares, and some of you have even managed to capture the biggest explosions the sun makes. It's staggering the detail that many of you can see using your telescopes.
Well, so far we've mostly been talking about the sun's surface, but it does of course have an atmosphere as well, and all sorts of things happen in that atmosphere.
And the atmosphere has a temperature of 1,000,000 degrees, which is too hot for the sun to contain it, and it streams out into the solar system, doing something similar to what happens when I blow up this balloon.
So what's coming out of the sun is a stream of particles called the solar wind. The sun is in the middle of Lucy's balloon here, and that solar wind spreads outwards. These particles push outwards through the solar system, and they form a shape pretty much like this.
That's right, so the solar wind is contained inside, and outside is the material between the stars. And sometimes the wind blows very strong and inflates this bubble.
Which we can demonstrate like so, very good.
And sometimes it blows more weakly, and the bubble deflates.
And just like there's air pushing down on this bubble to give it this shape, outside the solar system there are particles and the rest of the galaxy which shapes our solar system too. So this is the edge of the sun's influence on the rest of the galaxy.
And also, because the sun is moving through the galaxy, it's pushing against the material of the galaxy itself, and it creates a kind of teardrop shape that's compressed at the front and drawn out at the back, a little bit like this balloon.
And that's maintained by the fairly constant solar wind that the sun's pushing out all the time. But just sometimes we get a really spectacular event on the sun. The sun loses 1,000,000 tons of mass every second, and that mass streams outwards into space in the lumpy and gusty solar wind. Chris Davis studies that solar wind, represented here by his bubble gun. As material constantly flows outwards, because the sun and Chris are rotating, the result is a spiral pattern. Chris uses two spacecraft called STEREO to study a very special set of eruptions, coronal mass ejections, which are both spectacular and powerful.
Well, a coronal mass ejection, a typical coronal mass ejection, contains about the same energy as about 100 times the entire world's nuclear arsenal.
That sounds pretty scary.
It's an astonishing amount of energy. But a colleague of mine worked out before lunch once that it was also equivalent to the energy in a Mars bar if it were about 2,000 kilometres long.
Excellent. Well, I'll remember that. And so what's happening to these particles as they travel outwards through space? Are they interacting with the surroundings? Are they spreading out? How should we picture that?
Well, it's like a magnetic bubble which has lots of electrified gas, plasma, as it travels out. As that bubble expands, that gas is expanding with it, so it's getting more and more tenuous, more thinner as it comes out into space. Now, the solar wind is very few particles. It's about maybe 5 to 20 particles per cubic centimetre. So in a volume about this big,
there's only got 5 particles.
There's 5 particles, so it's almost nothing. And it's a really peculiar thing that this wind that is almost not there actually can slow down mass ejection as it emerges into it. And that's because these particles are electrified, they have magnetic fields with them, and so they can interact. They actually behave like a fluid.
In July last year, one of the Stereo spacecraft was temporarily blinded when a coronal mass ejection hit it head-on. The NASA satellite SDO was able to image the area of the Sun that eruption came from. If that had been in the direction of the Earth, it would have knocked out our mobile phone system, our satellites, and even our television. Not good news, but even the ordinary solar wind can have dramatic effects.
Luckily for us, we have a natural shield against these damaging particles coming from the Sun, in the solar wind and the eruptions, and it's our magnetic field. So similar in shape to the one created around this bar magnet, molten iron within the Earth creates a vast magnetic bubble extending thousands of miles above our heads. And normally the particles from the Sun flow around us. But sometimes our magnetic bubble gets energised and currents start flowing down onto the top of our atmosphere and lighting up the gases as they energise it. Oxygen shining green and nitrogen shining blue and red. And that's when we have the displays of the northern and southern lights, or the aurora.
The aurora borealis, or northern lights, are truly wonderful to look at. But the story of their origin has a violent and cataclysmic beginning. A huge coronal mass ejection erupts on the Sun, launching billions of tons of plasma out into the solar system in a magnetic bubble, and we are in its way. It slams into the Earth's magnetic field, and if conditions are right, our magnetic shield starts to open up and distort. This causes charged particles from far above our atmosphere to race down the Earth's magnetic field lines. They reach the top of the Earth's atmosphere, energising the oxygen and nitrogen particles and causing them to glow. It's this which creates the beautiful and mesmerising aurora borealis.
Last year, Lucy and I went to Svalbard in the Arctic Circle to see the transit of Venus. But we took some time out to visit the radar station, IceCat, which is looking way up into the top of the atmosphere, where the aurora dance day and night. Lucy explained to me how the aurora form.
The Earth is sitting in the Sun's atmosphere in this wind, and it's a bit like a pebble in a stream. And a lot of the time, the wind flows over the Earth's magnetic field. But sometimes when the conditions are right, the magnetic field of the Sun can connect to the magnetic field of the Earth. And so I visualise lines of magnetic field that break and join. And it happens when the Earth's magnetic field is pointing in one direction and the magnetic field coming in the solar wind is pointed in the opposite direction. And then the field lines can break and rejoin. The technical word is magnetic reconnection, which does what it says on the tin. It connects the magnetic field from the Sun to the magnetic field of the Earth and then channels those charged particles coming in the solar wind onto the Earth's magnetic field lines that ultimately can then spiral down and come to the skies above our heads here.
In Svalbard in summer, the sun never sets, but IceCat can still keep working. Aurora watchman Ian McCrea is at work right now, looking at the very top of our atmosphere, a region called the ionosphere.
Actually, we have had quite an active day, and there would have been aurora above your heads if it wasn't, well, there were aurora above your heads. It was too light to see anything, of course. But we've had a lot of structure in the densities and the temperatures that we've been measuring up in the ionosphere. And we've seen a lot of that this morning, quite structured heating, obviously structured electric fields. And we know that the global magnetic activity has been quite high. And in fact, it's a very favourable period for magnetic activity because the solar wind, the magnetic field in the solar wind has been pointed in the right direction for it to couple up with the magnetic field of the Earth, and that's what typically gives us these very energetic and enhanced events at these northern latitudes.
The effects of the solar wind spread out through the solar system and on out into space. And so to give you an idea of that scale, we've arranged some of the planets right across Greenwich Park. So Lucy, you're the Sun.
I have the Sun, which is at the centre of the solar system, around which all the planets orbit. It's a vast ball of gas with a nuclear furnace in its core, and it's spewing material out into space at millions of miles an hour.
The solar wind takes a few days to reach Earth over here, 93 million miles away, where the magnetic field channels it down to form the beautiful aurora. Much of it travels on outwards into the solar system towards Mars.
Millions of years ago, Mars had a much more substantial atmosphere, but it lost its protective magnetic field. So as a result, the solar wind slowly eroded away the atmosphere of Mars until today there's hardly any left. But the solar wind carries on out past Mars, right out to Saturn, where Pete is.
The magnificent ringed planet Saturn is nearly 900 million miles from the Sun. Now, Saturn has its own magnetic field, and that magnetic field interacts with the solar wind, and we get amazing displays of the aurora around the magnetic poles of Saturn. The solar wind doesn't stop there, though, and continues beyond Saturn, way out to the furthest planet in the solar system, distant Neptune.
The ice giant Neptune is 3 billion miles from the Sun, but that's not the limit of our star's influence. The solar wind streams past Pluto, which is bobbing around in the Thames somewhere, and onwards, more than 11 billion miles. We have probes exploring this region. The two Voyager spacecraft are heading towards Canary Wharf in our scale model of the solar system, and they're sending back information about what it's like at the boundary of our Sun's kingdom. The two Voyager spacecraft were launched back in 1977. They gave us our first close-up views of the ice giants, and are now approaching the boundary that marks the edge of our solar system and the start of deep space. This is the region where the solar wind is running out of steam, and you can easily demonstrate what's happening with running water.
Chris, I have here my mini solar system with the Sun in the centre and the planets in orbit around it, and then the solar wind blowing out from the Sun, reaching the edge, and the balloon represents the region where the solar wind stops. The Voyager spacecraft are close to that edge, and they've been finding some really surprising things. What have they shown us?
Well, they've shown us that the outer regions of the Sun's influence are very different to the way we thought they were going to be. So there's a demonstration we can do of what this region is like. Now, the water coming out of the watering can is the solar wind being thrown out from the Sun at 1 million miles an hour. So that's the start. And it spreads outwards, and initially it's a nice smooth ring. But when it gets to a certain point, the water, or the solar wind, slows down just enough and suddenly gets much more bubbly. You can see ripples and bubbles in it.
I can see bubbles around here. So there's a kind of circle, and then beyond that, where the water or the solar wind has slowed down, it's very bubbly.
Yeah, and that's the reason that the Voyager spacecraft are in now. And they've seen these bubbles. They were a complete surprise. We thought it was going to be nice and smooth, and there'd just be a gentle transition to interstellar space eventually, which they're heading towards. And these bubbles are absolutely massive. They're magnetic bubbles in the solar wind.
We don't know when the plucky, pioneering Voyagers will reach deep space, but their batteries will die in 15 years' time. Our journey to the edges of our solar system has also drawn to a close. The sun has set over Greenwich, and even though it's below zero, the Flamsteed Society have bravely joined us with their telescopes to keep us company. The green laser, which marks the meridian line, or 0 degrees longitude, is shining brightly.
Well, here we are, Pete. We're at Greenwich, and the lovely Flamsteed Society brought all their telescopes, but there's nothing to see because of the clouds.
What a typical sky at night.
So never mind. We do have something in February. An asteroid, see if I can remember the name, 2012 DA14.
You've been practising that, haven't you?
It's such a delightful name, isn't it?
It trips off the tongue,
It
yes.
does. Now, this is interesting because it's going to pass very close by to the Earth, isn't it?
Yeah, it'll pass us by about 35,000 kilometres. And when you bear in mind that geostationary satellites Those are the satellites which sit above the same point of the Earth. They deliver things like satellite television, for example. They're about 36,000 kilometres out. It's actually going to come within that.
So it's going to pass up in between them. Actually, we should stay. There's no danger of a collision or anything like that, and it doesn't rise up where we are till about 8 o'clock in the evening.
No, that's right.
But the best time to look at it is really around 9:30, 10 o'clock.
Yeah, I mean, this isn't a very large object. It's about 45 metres across, and that means that it will actually become bright enough to be seen with binoculars when it's at the closest point. But we're picking the point between 9:30 and 10 o'clock. Because that's the time when it crosses the tail of the Great Bear.
Right.
So the plough, or the saucepan as I call it. So if you locate the star in the upper left corner of the pan, and then the next one out along the handle, it's going to cross that line between 9:30 and 10 o'clock. Get with a low power eyepiece, should be able to pick it up. So go out and give it a try.
On special nights, the Royal Observatory welcomes the public to the dome of the 28-inch telescope, and Lucy and I joined that public tour. The 28-inch is over 100 years old and was the workhorse of the observatory, used every clear night to study the stars. Little's changed from those early days when astronomers had to lie on their backs to look through the eyepiece. The telescope was moved briefly to the darker skies of Sussex, but then, in 1971, it came home. Patrick and the Sky at Night were there to celebrate the return to Greenwich of this astronomical giant.
This is an historic moment at Greenwich Observatory. The great 28-inch telescope is coming home where it belongs, at the old Royal Observatory in Greenwich Park. Inside the observatory, everyone's waiting for the first of the really big lifts, the North Pier. And the mounting's going to exactly the same position as they had in 1857. And only after both piers have been firmly cemented down will the telescope, in its axis, be balanced and secured between them. It's not the end of the story by any means, because remember, it's going to be used, and therefore it's got to be very carefully adjusted, and this is going to take some time. But in the foreseeable future, it will be fully operative again, and it's good to know that the old Royal Observatory, Greenwich, has again got a great telescope.
The 28-inch is still used by astronomers today, no longer for research, but to enjoy the wonders of the night sky.
Tonight, as you know, it's a little bit cloudy out there, so unfortunately we can't peer through the clouds. It's the one thing that we haven't mastered as astronomers just yet. We haven't got control over the weather systems. But it does give us a chance to show off our biggest telescope here at the observatory, and also the 7th biggest telescope in the world of its type. It's a very special type of telescope called a refracting telescope, and there are 2 lenses at the very top of that instrument, and both of them together weigh 200 pounds.
This telescope is fabulous. It's wonderful to see it back after 120 years. It's so elegant in the way it moves around, so easy to move. I just wish it were clear so we could see something. Here's some footage of the moon taken through the 28-inch telescope, showing the Alpine Valley and the craters Archimedes, Aristillus and Cassini. I think Patrick would have enjoyed these.
We've had a marvellous time here at Greenwich, and a big thank you to the Flamsteed Society for turning out on such a cold, wintry night.
Next month we'll be up in Northumberland at the Kildare Observatory, hoping for better weather and to catch a glimpse of that asteroid as it whizzes past.
And we'll be bringing you the results of the Moor Winter Marathon, so well done to everyone who's taken part.
So until next month, from Greenwich, good night.
Stay with us tonight. The boys are in danger of getting their fingers burnt in Way to Go, coming up in 10 minutes. After a spot of music next.